Okay, you lucky dogs, here it is, our first Doodlecast of the year. I'm going to treat something really quickly that is on your problem set that's due tomorrow, Thursday, but we didn't get to go over in class, and that is the force on charged particles when there's more than one charged particle acting. It's really quite simple. All you do is you calculate the force on the given particle as though the other is not there, as though the third particle is not there. And then you do it again, and then you sum the forces. Here's a quick example. So how about this? What is the total force upon particle Q2 here, upon that one down there? What is the total force on it? Well, quite simply, I see that Q1 is negative and Q2 is positive. So the force on Q2 by Q1 is an attractive force. It's that way. And the quantity is KQQ over R squared. Okay? I also see that Q3 is positive, and it acts on Q2 as well. And since they're both positive, that's a repulsive force. So Q3 is also going to be pushing to the left. I'm going to try to draw it right here. So there's two forces. Force on 2 by 1. And there's a second force on 2 by 3. Okay, this program's a little bit causing me to write in a little bit more messy than usual, even because my hand has to hover above the iPad. Otherwise, my fingers start to make marks too. So anyway, all you do is you calculate the forces independently, and in this case, we're going to add them up. The signs are only used to determine if it's a repulsive or an attractive force. So I'm going to quickly run the numbers. I'm going to pause this while I do so you don't have to hear the tapping of the calculator, and then we will finish up. So when I run the numbers for the force on particle 2, the purple one in the middle, by particle 1, I get 9 E9, that's the constant, newtons times meters squared per coulomb squared. That's always the same, constant. Q1 times Q2, this is very important. 47 nanocoulombs is 47 billionths of a coulomb. And I multiply that by the other charge, which is 12 nanocoulombs, 12 billionths of a coulomb. And I divide that by the distance between them squared, which is 0.09 meters, and I square that. And so when I do that, I get a force of 6.27 E negative 4. That force is 6.27 E negative 4 newtons. Very small force. Okay, so I'm going to write that down here so I can erase up top and do more work. The force on 2 by 1 is 6.27 E negative 4 newtons. 6.27 E negative 4 newtons. And it is to the left. I think that's pretty clear because one's positive, one's negative. Now let me erase this and do the other particle. Okay, what about the other interaction? Because Q3 is pushing on Q2 to the left, and I know that because they're both positive. So all I do is I run the numbers again. Okay, so KQQ over R squared is 9 billion newtons times meters squared per coulomb squared. 9 billion times the product of the charges. So let's see, charge 2 is 12 nanocoulombs, 12 E negative 9, 12 billionths of a coulomb, that's a nano. And let's see, Q3 is positive 4 microcoulombs. Okay, so that's 4 millionths of a coulomb. 4 E negative 6 coulombs. Micro means millionths. So E negative 6 over the distance between them squared, 0.17 meters squared. And when I run this number, I get a force equal to 1.49 E negative 2. 1.49 E negative 2 newtons. Okay, so I've got one force down here to the left of 6.270 negative 4. I've got a second force, a much larger force because of a much larger charge on Q3, also to the left, and I know that because of the signs, and that's 1.49 E negative 2 newtons. And so the total force on Q2, I just add those two numbers up. So the sum of the forces on Q2 is 6.27 E negative 4 plus 1.49 E negative 2 newtons is 1.55 E negative 2 newtons. 1.55 E negative 2 newtons. And that is to the left. Okay? Had Q3 been negative, then that would be an attractive force, and the pull would have been that way. So then I would have had a completely different answer, of course. But again, the key point here is just do them one at a time. When they're all aligned, just do them one at a time, and then when you're done, just sum the forces as you would any other force interaction. Roger Dodger, over and out.